Clustering is one of the most powerful techniques in machine learning when it comes to deal with unlabeled or unsupervised data. In this video, we will discuss k-means clustering algorithm in details, and in order to make it interesting and practical, I will not use any abstract datasets or the datasets which are of limited applications. Here, we will concentrate on using word embeddings and applying k-means clustering. So word embeddings are very important in the field of natural language processing. And in order to start with embeddings, we will first import the SentenceTransformer library, which is a library containing large language models specialized for embeddings. Embeddings are the way to convert natural language into the multidimensional vectors. So we can convert a single word, a pair of words, or triplets of words, or entire sentence using large language models. As an output, we will update a numeric vector, which we can analyze later with various algorithms. So in this particular example, I will use 10 pairs of words, which are grant access, revoke access, access profile, add user, delete user, modify user, and create user. Finally, disk space, disk full, and disk error. So you can guess that these key phrases coming from some different classes of sentences, and they represent a particular messages of a certain class. So for example, grant access, revoke access, and access profile can be attributed to some sentences or messages or tickets which are related to the access. All the user-related pairs can be attributed to some user-related activities, again, like support tickets or administration rules and so on. And finally, disk space, disk full, and disk error can be attributed to some context which is related to the disk space, disk capacity, and so on. Indeed, these 10 pairs coming from the support ticket dataset, which is designed to show the end-to-end pipeline of how to deal with the natural language processing in the context of support tickets. However, in this video, we will only use with words. If you want to dive into all the details how these pairs of keywords were obtained, you can visit support ticket classification notebook, and also you can directly investigate support ticket dataset. So once our SentenceTransformer model has been loaded, we will go ahead and apply this model to obtain embeddings for our pairs. For this, we will call the model, encode, and provide pairs as an argument. We can see that embeddings has the shape of 10 and 768. So 10 is a number of pairs which we have. So we can see that each pair has been converted into 768 dimensional vector. Usually 768 dimensional vector is a vector size for the embeddings of base BERT model. In contrast, there is a large BERT model, which is using 1024 dimensional vectors for embeddings. However, in this case, the basis model for all MPNet base v2 is a base BERT-based model. Therefore, we have the output of 768 dimensional vector. Next, to make this data a little bit more understandable and more feasible for visual analysis, we will perform a dimensionality reduction. For this purpose, we will use principal component analysis from scikit-learn library, and we will boil down 768 dimensions into 2 dimensions only. This way, we will be able to visualize these embeddings in 2-dimensional space. So here we import principal component module from scikit-learn library and apply the transformation to embeddings of our pairs of words. Next, for the future exercise, we will define centroids, which will be used later. Now, we will visualize our points in 2-dimensional space, and here we can see how these points are distributed. So let's have a closer look what we can do with these points. We know that revoke access, grant access, and access profile, these keywords are derived from a context about the access. Modify user, delete user, add user, and create user are derived from the context of user management. And disk full, disk space, and disk error are derived from their hard drive or disk management context. In the semantic of language, these keywords seem very similar within the groups rather than across the groups. What I mean is that revoke axis, ground axis, and axis profile are more similar in context of a natural language than other pairs. Furthermore, disk full, disk space, and disk era are also more similar to each other in the context. And finally, delete user, modify user, add user, and create user are more similar to each other than other keyword pairs. We can see that in two-dimensional space, the embeddings for each of the groups of these keywords are closer to each other within the group rather than the embeddings across the groups. So now we would like to come up with the algorithm which will allow us to do this grouping or clustering in an automatic way. And with a method we are going to apply is called k-means clustering. The idea behind the k-means clustering is as follows. We should define a number of clusters. We should define a number of clusters before the start an analysis. So in this case, we will assume that we should have 3 clusters, and each cluster will be characterized by 2 things. So first of all, each cluster will have a center. So we will have a centroid point. This is 2-dimensional point, which will be a center of the cluster, and we set it randomly. So we will have 3 centroids. These centroids are marked with red, green, and blue cross marks. Now, when we can see the location of the embeddings of the keywords inside the 2-dimensional space together with the centroids, we would like to assign these embeddings to particular clusters or group them. In order to do that, we should perform 2 steps. First step is a cluster assignment step. We will assign embeddings to particular clusters by the following rule. We will compute a distance between a given embedding. For example, it will be delete user, green centroid, red centroid, and the blue centroid. So the Euclidean distance in this case is a measure of similarity. The closer embedding to the centroid, the more similar it is. And we will perform this operation of computing the distance between each embeddings and cluster centroids. Then we will select minimal distance. So for example, in this case, the minimal distance is between delete user embedding and the green centroid. And to doing this, we will assign indices to the centroids. And once we find out that a given embeddings has the minimal distance to a particular centroid, we will assign the index of that embedding to that cluster. Now let's go ahead and check the code. So the first step is a cluster assignment step. We will import SciPy library, which will allow us to compute Euclidean distance. We also have a detailed video about Euclidean distance computations and the meaning. You can find it in the description below. So now we'll create a loop for all the embeddings, and we will get the index of embedding. Inside the loop, we will go through the centroid values, which are stored in centroid dict variable. We will compute a Euclidean distance between each embedding and each centroid, and then we will compute a square root of Euclidean distance. Then we will find the minimum distance and get the index of the minimal distance. So in this way, we will understand which cluster we should assign given data point or given embedding. Let's have a look on the actual run of this code. So first, we will take a data point which corresponds to a ground axis. In 2-dimensional space, these embeddings look like this vector. We have 3 centroids. First is 0, 0.4. Second is minus 0.2, 0, and the third one is 0.4 and minus 0.1. The distance between these embeddings and all the centroids are as follows. And the minimal distance is 0.578. Therefore, this is cluster 0, and when we assign ground axis embedding the cluster 0. The same way we are doing for all the remaining 9 points. In total, we repeat this computation 10 times. This is cluster assignment step. Here you can see that of the first run, the revoke axis and ground axis, they are closer to red cluster rather than to all the others. The closest cluster for disk error, disk full, and disk space is blue cluster, and in the closest cluster for access profile, delete user, modify user, add user, and create user is green cluster. And as you can see that in this case, access profile, we would expect to be related to the red cluster. However, in this case, it belongs to green cluster. However, this is only the first step of the k-means clustering algorithm. Then, so the second step is centroid update step. What happens here is once we assign data points to the cluster, now we will update the centroids themselves. In order to do that, we take an average across all the data points within given clusters, and we will assign that average to be a new centroid. So in this case, the centroid should move to a new location. So let's perform a centroid update step and see how centroids change after that. Here I also define some auxiliary variables. So centroid dict in time is a dictionary which will track the centroid dictionary variable, which contains a dictionary of centroids. So we have a key value of 0, 1, and 2, which corresponds to our cluster indexes. And for each cluster, we will have a value of a centroid, which is a two-dimensional vector. So this is how the centroid dictionary is organized. And then for each iteration or for each epoch, we will record the centroid step. On the other hand, we will have another variable called centroid in time. In this case, the keys of this dictionary will be indices of the clusters. However, as a value, we will have a list which is tracking different values of centroid for a certain cluster across the iterations of epochs. I will explain what iteration and epoch means in the following context. So let's run the code, and we will see how our centroids will change. So the original value, the red centroid, was here, and now it's moved in the middle of revoke axis and grant axis embeddings. The original value of centroid 1, or the original value of green centroid, was here, and now it's moved somewhere inside the triangle between modify user, delete user, and add user. You can see that access profile is kind of already an outlier for the green cluster. And then finally, for the blue cluster, blue centroid moved from its original place inside the triangle of disk error, disk full, and disk space. So now, the cluster assignment step and centroid update step together constitute a single epoch or iteration. So this is iterative algorithm. The more iterations we perform, the more stable the centroid values should become. So now let's run multiple epochs. For this purpose, we will update the code slightly. We'll take our cluster assignment step code and cluster update step code together. We'll wrap it in a for loop for the number of iterations or epochs. And also we will redefine the centroid dictionary with initial values of centroids, and we will redefine centroid in time, centroid dict in time, and clusters in time. For clusters in time dictionary, we will have a keys as iterations, and for each iteration, we will store the structure of the clusters. In other words, we will map an index of a cluster to the list of the data points which belong to this cluster. So let's run this code for 3 steps, and we will investigate the results. So now we have 3 iterations, and now let's inspect our cluster dictionary. You can see that cluster dictionary contains 3 keys, 0, 1, and 2. These are indices of our clusters. The 0 cluster contains entries 0, 1, and 2. The second cluster contains inputs 3, 4, 5, and 6. And the third cluster, which has index number 2, contains data points 7, 8, 9. Now, if we have a look at the centroid dict in time, we will see how the cluster centroids evolve in time. We begin with our initial values for the centroids. This is our -1, or iteration -1. After the first iteration, the centroid values are updated, and it's significantly different from the original values. Then for the second iteration, we can see that for the second cluster, centroid value almost doesn't change, but the values are changing for the first cluster with index 0 and second cluster with index 1. And finally, we can see that during the second iteration, none of centroid values has been changed. And that is an indication that our algorithm has converged. Now let's have a look at the centroid in time. It should have 3 keys. So this is our history of centroid for cluster 0. Centroid in time dictionary represents a history of updates of centroid values. So first we have our initial value. Then this is the value after the first iteration, this is the value after the second iteration, and this is the value after the third iteration. And similarly for cluster with index 1 and cluster index 2. Clusters in time dictionary contains the evolution of how data points were distributed across the clusters. For example, for the first iteration, cluster 0, which is our red cluster, contains 2 data points, 0 and 1. Cluster 1, which is our green cluster, contains 5 data points, 2, 3, 4, 5, and 6. And cluster 2, which is our blue cluster, contains 3 data points, 3, 7, 8, 9. On the next iteration, cluster 0 contains 3 data points, cluster 1 contains 4 data points, and cluster 2 contains 3 data points. And the same cluster structure appears after the second iteration. Next, let's visualize evolution of centroids across epochs. Here they can see how centroids for the red cluster, yellow cluster, and blue cluster has been evolved during the K-means clustering training. Finally, let's show how clusters are arranged in two-dimensional space. So this is our clusters, and we can see that indeed access, profile, grant access, and revoke access belong to one cluster. Modify user, delete user, add user, and create user belong to another cluster. And disk array, disk full, and disk space belong to the third cluster. And to summarize, let us also highlight the size of each cluster by drawing a circle around each cluster. For this purpose, we will need a maximum distance in order to use it as a radius for the circle size. So we will compute the distance between the center of each cluster and between each data point in that cluster. Then we find the longest distance and we will use it as a radius. So here we can see the maximum distance for cluster 0, 1, and 2. And finally, let's draw the circles around the clusters. This concludes introduction to K-means clustering with embeddings. In the next videos, I will explain how to measure the quality of clustering, how to decide number of clusters, and how we can next connect together Euclidean distance and a probability, and how we can use the same logic which we use to design K-means clustering code for designing Gaussian Mixtures model, which will use probability as a similarity measure. Also, all the code is available in the repository. You can find the link below. You can also check the original support ticket dataset. This concludes introduction to the K-means clustering. Please stay tuned, like and subscribe, and see you soon in the next videos. Gaussian mixtures or mixtures of Gaussian distributions is a very popular method for estimating probability distributions. However, that also can be used for clustering. One of the most famous applications of Gaussian mixtures is anomaly detection. Today we will talk about the Gaussian mixtures for clustering. In our previous video, we have discussed K-means clustering in great details, and we finished with showing the sizes of clusters. So here we are. We have the centers of the clusters, and we have the circle area around each center indicating the size of the cluster. In this case, size of the cluster is a distance between the center of the cluster and the most distant point. In other words, this is the maximum distance between the cluster center and the points in that cluster. Plus, we also added a small delta for visualization purposes. So the question now is, so in the case of K-means clustering, we used the Euclidean distance to do the clustering and compute the similarity of the points. And now we can see that this Euclidean distance also represents the size of the cluster. However, they don't really feel the Euclidean distance. What is that? For us, it's just an abstract measure, which is showing the similarity. Can we extract more information from this Euclidean distance rather than just computing it? Can we apply more meaning and more value to that? And the answer is yes. We can connect the Euclidean distance and the probability. So we can not only compute the distance between the centroid and the data point within the cluster, we can also compute the probability of that given data point to belong to the cluster. How we can do it, I will show shortly in this video. So first we will come back to our original setup, and we start with Gaussian mixtures. At first, we import all the necessary libraries, and as in the previous case with K-means clustering, we will apply our clustering for embeddings. So embeddings from the support ticket dataset, we have extracted 10 pairs of keywords from the dataset. Grant access, revoke access, access profile, add user, delete user, modify user, create user, disk space, disk full, and disk error. How to extract these keywords and what is the meaning of these keywords, you can learn by referring to another video, which is especially dedicated for support ticket dataset classification. Also, you can find K-means clustering video in the description below. So then working with embeddings, we've started off importing SentenceTransformer library, which will be our main library to deal with transformer large language models in this video. Then we use these 10 pairs of words and load the model, all MP-NET base version 2, which is BERT-based transformer model. And then we encode our pairs using this model, and we get the embeddings for our pairs of words, and we can check the dimensions of these embeddings. So it's 768. 768 come from the native dimensionality of embeddings for BERT-based models. The next step is to apply dimensionality reduction, and we will shrink these 768 dimensions into 2 dimensions. This will help us with visualization of our data. In real scenarios, for enterprise analytics, you can apply all 768 dimensions. However, for the purpose of this lecture, we will stay in 2-dimensional space. We will also create our centroids, so you can create it randomly, or as we did in our previous video, we will select some good centroids at the very beginning. Then we can visualize our data. So these are our embeddings with assigned pairs and the index of the pair in the list. And finally, we can visualize it together with the centroids. Until this point, the steps are the same as we did in the previous video. Now, let's discuss Gaussian or normal distribution and how we can actually make a transition from Euclidean distance, which explains us the distance in the space between 2 points, to probability. So the formula for normal distribution is as follows. And we have a component where we make a of exponent in power x minus mu square divided by 2 sigma square, and this fraction comes with negative sign. So x would be our input, and this is a scalar value. Mu is our mean value for the normal distribution, so this is also scalar value. And sigma is our standard deviation. So when they square sigma and getting sigma square, this is our variance of the normal distribution. And the first part is a normalization coefficient, 1 divided by sigma square root of pi. And immediately we can see this interesting component, x minus mu square. So technically, in one-dimensional space, x minus mu square is a squared Euclidean distance. So now we can see how we can use Euclidean distance to squeeze more information from the spatial locations or spatial distance of 2 points and get the probability value out of that. So let's plot the probability of one-dimensional normal distribution. Here I provide 2 examples, and key feature is that we draw our graphs on the basis of the intervals starting from mu for each distribution minus the standard deviation value, which is our sigma. We scale by 3.5. So this range of 3.5 contains almost 100% of the entire probability density for the normal distribution. Here you can see 2 different normal distributions with different parameters. So the first blue line, as normal distribution is called bell-shaped curve, is for mean value 0 and standard deviations 1. The second normal distribution is for mean value 3 and standard deviation 2. Problem related to normal distribution is we expect this normal distribution density function to output values not greater than 1, because by definition probability cannot be greater than 1. However, as you can see, if we fix mean value and set mu equals 0, and then we will start reducing the standard deviation value, then between sigma value equals 0.6 and sigma value equals 0.5, we will actually cross this unit line. So our probability value will be higher than 1. And this is especially true for the small values of sigma. So in this case, we cannot consider this as a probability anymore. So what we have to do is take all the values produced by this distribution and normalize it. So basically take the overall sum of those frequency values and divide each frequency by the total sum. In this case, we will take it back to the probability space. This will be also true for multidimensional space. So now let's have a look what happens in 2 dimensions and higher dimensions, in n dimensions of space. So in n-dimensional space, instead of scalar values, where we will have our x as a scalar value of dimension 1 by 1, we will have x to be a vector of dimension n by 1, and also mean of the normal distribution will be n by n dimensional vector. So in the terminology of linear algebra, these are column vectors. So we have n rows and 1 column. On the other hand, standard deviation sigma from scalar value is turning into n by n dimensional matrix. And the structure of that matrix is along the diagonal, we will have a covariance between the variable of the same dimension. So basically dimension 1 with dimension 1, dimension 2 with dimension 2, and so on. And of the diagonal, we will have a permutation of covariances of the given dimension. So for example, dimension 1 with dimension 2, and so on up to dimension n. So this should be a square matrix. Also, covariance of the variable with itself is known as variance. So along the main diagonal, we will have variances of the numbers in a given dimension, and of the diagonal, we will still have covariances. In case of 2 dimensions, our covariance matrix is having this representation. So we have sigma 1 squared and sigma 2 squared along the main diagonal, and we have covariance between the first dimension and the second dimension. So scalar value of variance or standard deviation is now turning into matrix, and we call it sigma capital n by n. The probability density of normal distribution in n-dimensional space is as follows. Again, we have this normalizing fraction in the first place, 1 divided by 2 pi in power n divided by 2 by square root of determinant of the covariance matrix. And then we will have our exponent in power of half of x minus mu vectors transposed multiplied by inversion of sigma capital matrix, our covariance matrix, and multiplied by x minus mu. So let's do a small correction. Dimension of x is n by 1, not n by n. So what is this our value for the exponent? This multiplication of x minus mu transposed by inverted covariance matrix by x minus mu is known as Mahalanobis distance. We should compare this Mahalanobis distance with Euclidean distance. By definition, Euclidean distance is sum of square differences component-wise between two vectors, which can be also written in the form of x minus mu transpose multiplied by x minus mu. So the first component of Mahalanobis distance and the third component of Mahalanobis distance are basically components of Euclidean distance. And in the middle, we have inverted covariance matrix. Covariant matrix, for example, in two-dimensional space, you can consider as scaling and rotation matrix. The values on the main diagonal will introduce how much the distribution is extended along x and y axis, and covariance value will manage the rotation. We will see this shortly in the example below. So Euclidean distance is the basis and Mahalanobis distance is extension of Euclidean distance. Therefore, both one-dimensional normal distribution and n-dimensional normal distribution use the notion of distance in order to compute probability. And this is the key relationship between the distance and probability. So here is an example of covariance matrix. In this case, the variance along each of dimension is the same, while covariance is minus 0.5. Here we also introduce a function to compute multivariate Gaussian distribution. So we have a position or x value as input, mu as mean vector, and sigma as covariance matrix. And here we can see two examples. I use two cases, the same mean value, 0.0. So x-coordinate is 0 and y-coordinate is 0. However, in the first case, we have our covariance matrix with 1 and 2 on main diagonal. So we do not scale the x dimension, but we extend y dimension twice. And we also use covariance 0.5, which gives us rotation. In the second case, the mean value is the same. However, we apply zero covariance and the same unit variance in both cases. And you can see that the xy section of the first probability density looks like concentric elliptical section. So we can see that this section is extended along the y-axis and it is also tilted. So the tilt is the effect of covariance value 0.1, and extension along the y-axis is the effect of variance equal 2 for the y component. However, you can see that in the second case, both scale values for x and y components are equal to 1, and in this case there is no extension along either of x's, and covariance is 0, so there is no rotation of the probability density. I hope this helps to simplify the understanding of two-dimensional Gaussian distribution. Now let's talk about the Gaussian mixtures. We now can operate normal distributions, and instead of applying just a single normal distribution, we can use a mixture of Gaussian or normal distribution. In this case, we will assign weight Pi for each ith component. So for example, P1 for first component, Pk for k component. And we'll also give the same indices for mean value and standard deviation. In this case, we consider mixture of one-dimensional normal distribution or Gaussian distributions. The important point here is that the sum of all p-weights should equal to 1. In the case of n-dimensional or multi-dimensional Gaussian distribution, the structure will be the same, except for now we should use different mean vectors and covariance matrices for each component. So let me illustrate how one-dimensional Gaussian mixture looks like. So in this case, we have two components. First component has mean value 0 and variance or standard deviation 1. The second component has mean value 3 and standard deviation 3. We mix them with coefficients both equal to 0.5, and the red line is our Gaussian mixture. So how we can use these Gaussian mixtures? One of the most popular methods to use Gaussian mixtures is called EM algorithm. I will have a separate video to explore EM algorithm in depth. At this point, we will only need understanding of the general structure of the EM algorithm and what happens in each step. So EM algorithm is expectation maximization algorithm. And the first step is expectation step, where for each data point, we compute probability to belong to each component of a Gaussian mixture. And then we select the maximum probability and assign a data point to a corresponding mixture component. During the second step, we update values for mean vector, covariance matrix, and weights. So in order to compute a new mean vector, we will take all the data points assigned to a given component and compute the mean value of these data points. In order to compute covariance matrix, we will take all these data points together and we will compute covariance matrix for all dimensions. And finally, weights are computed as a ratio of number of data points assigned to a given component to the total number of points. So for example, if we have 100 data points under consideration, 25 of them are assigned to a given component, then weight for that particular component should be 0.25. EM algorithm resembles the steps of the clustering k-means algorithm, which we have learned in the previous video. So the first step for clustering was cluster assignment step, and we can see that expectation step of EM algorithm is exactly a cluster assignment. We use probability to belong to a particular component as a measure of similarity between the data point and the Gaussian distribution. So in a sense, now instead of introducing a centroid of our cluster as just a center data point, we represent the centroid with the data point itself and the covariance matrix, which is associated with that data point. So now we have to initialize the mean values, which will be our centroids from k-means clustering. And we also should initialize covariance matrices for each of centroid points. In this way, we have to do a small update to our code and we can visualize the clusters. Now, instead of just having center points or centroid values for our clusters, we will have centroid values surrounded by the elliptic shape, which are representing covariance matrix. As our variance values are very small in this case, we should expect two following things. So first of all, the value produced by the probability density will definitely be higher than 1. So we should rescale that if you want to operate in the probability space. However, this is not really necessary in this case because we just need some values and that should be necessary probabilities.
And the second observation is that these elliptical forms or elliptical shapes should be extended along y-axis. And the third observation also, since our covariance between the dimensions are zero, there should be no tilt for these elliptical forms. And one more final observation is, since the variances are very, very small, we will not be able to use them directly to visualize. We have to scale them. And in this case, we scale these variances by a factor of 100. So what we see in this graph is basically 100 multiplied by variance along a particular scale, along a particular dimension area. So this is how it looks like. So this is 100 sigma along y dimension and 100 sigmas along x dimension. After we understand how the clusters are now represented in the case of Gaussian mixtures clustering, we need to change the code for cluster assignment step. Previously, we were using Euclidean distance as a measure of similarity. Now we use Gaussian probability, or probability produced by the Gaussian probability density function, as our measure of similarity. And in contrast to distance, the higher the probability, the higher the similarity. In case of distance, the longer the distance or the higher the distance value, the smaller the similarity is. So we use multivariate normal.pdf function from SciPy library to compute multivariate normal distribution. And as I mentioned previously, instead of argmin, then we were using to select the minimum distance. Now we want to use argmax in order to select the maximum probability value. And this is pretty much the only changes we have to do to the code in order to implement Gaussian mixtures. We'll have a similar output as in the case of K-means clustering. We will have the centroid values, and for each data point, we will compute output of probability density functions, and then we will select the highest one. So here, 2.67 in negative 21 power is obviously the largest probability across all the others. And this is done for all 10 data points. So we can illustrate how the data points are assigned to different clusters or components of Gaussian mixture. The second step, once we are done with distributing the data points across the probability distribution components, or aka clusters, we should update the parameters of the clusters. And in case of K-means clustering, it was a centroid update step. In case of Gaussian mixtures, this is maximization step. So these are two same steps in a nutshell. Here we define additional variable, which is covariant dicted time. Here we will basically store the values of covariance matrix across the iterations. And also, we should add the computation of the covariance matrix. So first we compute the mean values of dimensions for all the data points assigned to the given cluster or Gaussian component. And second, this is a new part, we will compute a covariance between all the dimensions. In this case, we have only 2 dimensions, so we will compute covariances between those 2 dimensions, and we will have 2 by 2 dimensional covariance matrix. So we will update the centroid values or mean values, and we will update our covariance values as well. This is our centroid update step. We do not use weights values for Gaussian mixtures. In this case, we just drop this part of computation. And finally, we can show how our originally initialized clusters change after the first step. So you can see that the red cluster now has essentially smaller variance along x dimension and almost no rotation, so covariance is very close to zero. However, there is essential covariance component in case of a green cluster, and it's very strongly extended along the y-axis. And the same is actually happening to the blue cluster. It is essentially tilted, that is essentially extended along the y-axis. So these are our two steps of cluster assignment step and centroid update steps. In the case of Gaussian mixtures, or if we use Gaussian distributions instead of just centroid points or the mean points for the clusters. And here is the illustration of update of covariance matrix. Basically, that explains this figure, how the elliptical shapes before update and after changed. This can be seen straightforward from this covariance in time dictionary. Now, as in the case of k-means clustering, we will run our algorithm for multiple epochs. In this case, there will be 3 epochs. And we can see the result of the clustering for 3 epochs. So first of all, we see our cluster dictionary. So cluster dictionary in this case contains 3 keys corresponding to each of the clusters. And we can notice that there is no big change from our original assignment. Also, we can check how centroids change in time. So this is our centroid dict in time. So this is our centroid in time dictionary. In this case, we are storing the history, how some mean values of centroid changes across the time. So it is not a dictionary, it's a list of centroid values. And you can see that they almost don't change across all the iteration after first iteration. And finally, clustering time, it's also the same. So there is almost no change in this case. So finally, let's visualize our clusters. So this is evolution of the centroids. You can see that we hit the center values for the clusters pretty much quickly, similar to the case of the k-means clustering. And now we can go ahead and visualize clusters with connections between the data points and the clusters. And finally, we can show resulting clusters as Gaussian probability densities. So here you can see the final clusters and their representations in the form of mean value and variance matrix. This is our final representation of clusters after applying Gaussian mixture clustering. Then we represent each cluster as Gaussian probability density. So this concludes the discussion of how k-means clustering can be extended to get more information and use Gaussian probability to enrich the clustering algorithm. So in the coming videos, we will discuss EM algorithm in greater details. And also, I'm planning to make a separate video for in-depth discussion of Gaussian probability density function and the Euclidean and Mahalanobis distance, which make it possible to connect probability and physical distance and dimensional space. So this concludes Gaussian mixture clustering topic. So stay tuned, like and subscribe, and see you in the next videos. Thank you.